So welcome back everybody after a nice and well-deserved coffee for the second seminar of today. So it's really my pleasure to introduce Professor Hideyuki Sawada from Waseda University. So Waseda University is one of the key partners of ULB University around the world. There are several collaborations ongoing, and Professor Sawada has been here with us for several weeks, collaborating and chatting around with various groups. And I'm very curious to look at his presentation. It is about robotics and machine learning techniques for understanding, controlling, and predicting physical phenomena. So I leave him the stage, and thank you for coming.
Thank you very much, Emmanuel, for the kind introduction. Okay, my name is Hideyuki Sawada from Waseda University. Okay, today's my topic is this one, robotics and AI. And firstly, I briefly introduce Waseda University. Our university is situated in the middle of Tokyo, and you see, yes, and Tokyo is here, and Osaka, and currently Osaka Expo 2025 is going on. And the Waseda is here, and this is a map in Tokyo Metro, and you see here, this is Tokyo, and our Emperor's house is situated just next to Tokyo Station, and here Shinjuku. You see in Shinjuku Station, every day about 3.5 million people are using this station. Yes, in the station, and the Waseda University is situated just close to Shinjuku. There are only 2 stations, about 3 minutes from Shinjuku. Oh, okay. I see. I have to use. Oh.
Yes.
What? Maybe this microphone.
No, please.
This one?
No, please use the...
Oh, okay. This one.
Yes.
Okay. I see. Okay. Yeah, I understand. Okay. Yes, the Waseda is here, and our campus is directly connected from the subway station. Just get to the station from Shinjuku, only 3-4 minutes, then go up, then my building. Yes, and Waseda is a university, a private university in Japan, and leading university, especially specialized with robots, human-sized robot and robots. And we have about 40,000 students in undergrad and about 10,000 students in graduate school. And so far we have many prime ministers in the alumni of Waseda University, and also business leaders and CEOs of big companies in Japan, like Sony, Casio, Lotte, ANA, Honda, and so on. And we have some rankings in Japan, not in the world, in Japan. We have the first one in Japan in many subjects. And also we have many collaborations in all over the world. And you see in Brussels, ULB, we have our university has a Brussels office in ULB. And we are encouraged to have a good collaboration with Belgian universities, especially ULB, VUB, and so on. Okay, and here about the history of robotic research to be conducted that have been conducted in Waseda University so far, and more than 50 years ago, Waseda University invented a human-sized biped robot, firstly in the world. The robot. I will show you the demonstration video later. And then in 10 years later, we again introduced a piano-playing robot like this. And it was exhibited in Tsukuba Expo, held in 1985, 40 years ago. And after we started a humanoid project for the development and research for human-sized robots to support and to work with. And so far we have developed many kinds of robots so far. And this is some robots that have been developed in our university until 2000. And then later in the 2000, okay, yes, maybe, okay, this one, okay. Let's, oh, no sound. No sound. Oh, okay. Yes, this is the first robot to maybe, yeah, like this one, 50 years ago. The first robot 50 years ago that we have developed is the static walking robot. It means that in each small motion, the stability is calculated. Then in any situation, the stability is robot was kept under the control. But this kind of stability, static state walking is different from us human walking, because we are walking like this dynamically, right? So we cannot stop on the way of the motion, right? So you fall down. Then, but the first robot was realized by the static motion one by one. And at that time, the robot took about 30 seconds for one step, because we need some calculation one by one. And the first robot used the hydraulic system, right? Not the electric motor. At that time, there was no such motor, right? Then, and the second one, that was developed in 10 years after that, we realized the dynamic walking, just introduced here. Maybe not this one. Okay, like this one, dynamic motion, walking motion, like human, and also it can climb a little bit, climb up steps and some slopes, like this, more than 40 years ago. And after, we developed a piano-playing robot by using DC motors, with maybe 30-some or more, DC motors for the control of the fingers and the feet for playing keyboards. And in Tsukuba Expo in 1985, this robot co-played with the real orchestra. Maybe we are like this one. It was really a sensational work realized by robot 40 years ago. Yes. Yes, right. Yes, this is an old video, but this is the history. Okay, then in 2000, we started another robotic research institute called Future Robotics Organization, and we have developed further robots, not only just to walk or make move, but to handle some objects or to make a collaboration and a communication, including touch with human. And this is a video of a robot about 10 years, developed 10 years ago, around 2010 something, sometime about 10 years ago, and it can dexterously manipulate the small stuff. It is a chopstick, and it can handle it to. No, it is not a chopstick, but a straw. To put it in a cup, to give it to another person, right? And also, this robot is able to break an egg, maybe this one, like this. Yes, dextery, yeah. Like this, maybe like this, okay. By controlling the force given to the eggs, the robot is able to softly grasp the egg, and also it gives some force to break it on a pan. Okay, right? And yes, the walking robot. As you know, these days there are different kind of or a bunch of robots introduced by the U.S., of course in Japan and also China. But as I introduced, the first biped robot was developed by Waseda University, and these days the different kind of robot is developed. But we Waseda, group do not work for biped robot anymore because this is a typical structure of the biped robot. The biped robot is expressed by the physical control model of an inverted pendulum, right? Then all the motors are settled in the inverted pendulum, but it is much complex, but it can model like this. Then by modeling all the models and the geometrical structures of the robot, we can construct a control system. Then once we get a control model, it is not difficult to control it. What the problem of these days is the power of the motor to generate power. It is because, have you ever think of how much force is given when you walk? For example, 60 kilograms person, when you walk, how much force is applied to, for example, in a knee? Have you considered that? About 4 to 5 times of your weight. This means that the 60 kilogram person, when he walks, about 200 kilograms force is applied to the knee or of the foot. Then to make a similar motion by robot, the motor in the knee or the ankle has to generate such strong force and real time. But luckily, it is possible to obtain such motors thanks to the development of the motor companies. Then these days, this kind of biped robot is able to make a pretty quick running motion or jumping or something much complex. It is, of course, it is the real results of the control systems of the feedback of motor systems, but also the development results of the pretty strong motors to generate force in real time. But we have developed, we have been, Waseda University has been engaged in the development of such robots so far. And these days, we are much interested in the further flexible robot to be able to have a good communication with human. Yes, for supporting or for having interaction in real time with a human, like to give to hand some object to a person or to work together or something more. Okay, as you know, robots have been firstly introduced for the manufacturing in factories, right, in a secondary sector of industries. And then such robotic technologies have been introduced to primary sector of industries, such as agricultural robots, or agricultural worker supporting robots and something more. And also, these days, such robots have been further developed in the tertiary sector of industries as a service robots to support human or to assist human and something more. And this is another result introduced by the graduates of Waseda University. It is a project called Gundam Global Challenge. Gundam is a very famous robot, firstly animated in Japan in 1970s, almost 50 years ago. And all Japanese people knows it. And about 10 years ago, we started, the company, animation company, and some companies got together, including the graduates of Waseda University, alumni of Waseda University, to develop the real-size Gundam robot. The Gundam robot in the animation, it is introduced as a 10 times taller, 10 times size of human, and it fights with enemies, right? And then we started a project to develop the real-size Gundam to move, not only a statue, but the move. Okay, right? Yeah, this is a result. the robot was introduced to open public in 2021. In fact, the robot has been, this project started to introduce this robot for the Tokyo Olympic Games to be held in 2020. But due to the corona situation, it was extended 1 year later. Then the robot was open to the public in 2021, 4 years ago. Okay, this one, it moves. Okay, you see, these are the people. Yes, 1/10 of the robot, and they observe the robot from the top. Okay, the height is 80 meters, as introduced in the animation, and the weight is 25 tons, because if person with a weight of 60 kilograms, when the guy becomes 10 times taller, what will be the weight? The calculation is cube, right? 10 times, 10 times, 10 times, 1,000 times heavier. It means that the 60 kilograms person, if he becomes to 10 times greater, the weight should be 60 tons, right? As you know, we human beings do not have motors to generate such great, amount of force, right? So we did something to realize it. Okay, yeah, this is a robot, and it's me, and he's a doctoral student in my laboratory, and this is the size of the robot, and you see the robot moves like this. Yeah, this is a demonstration of the motion of the robot. It moves very slowly because each motor has a quite great amount of gears to amplify the generated the power into the outputs, right? So the gear make the motion slower in proportional to the gear ratio, So the motion is very slow, but it moves. Even the hand part, the robot is raising his arm like this. But the weight of the arm itself is several hundred kilograms. So this means that, and also it is just the weight. But if you make it if you make the arm go up, then the motor of this part works. It means that the force to be given from this motor has to be calculated with a moment, right? Proportional to the distance, right? So the force should not be only the weight, but also the torques. So the several times of the several hundred kilograms. So like this. Yes, pretty heavy arm to be going up like this, but it works, right? And the Gundam has been exhibited in Yokohama, next to Tokyo, from April 2021 until March 2024, just until 1 year ago. Then in March of 2024, we disassembled it. Then what happened? They were sent to Osaka Expo. Okay, here. And currently, this robot is exhibited, not moving, but it is exhibited like this, in a still pose like this, in Osaka Expo. So if you go there, you can see the Gundam, but the real size Gundam, 80 meters height, but it won't move anymore. Yeah, like this. In a pavilion, they exhibit the Gundam. Yes, and then in the pavilion they present some metaverse exhibition in this one, so that you can observe the Gundam only in a 3D or something in this pavilion. Yeah, and the outside we exhibit they exhibit this Gundam. Okay. Yeah, currently until maybe September of this year, I don't know. Yes, maybe 3-4 months from April, this month. No, last month. Yeah. Okay, then, okay, so far in Waseda University, different type of robots has been introduced so far. And we have realized that the robot, the robot in factory can be, sent out to, home for open public so that it can work with human in a human living environment. And then such robot cannot be specialized with great power or fast motion or something more. They are not. They will not exist. They will not exist for fast production, mass production, or very precise motion or something more. Instead, the robot should behave like human, because we human do not move such precise, such fast. But to work or to live with human, the robot should be like human, right? And so to do so, the one approach to be installed in robot is machine learning or AI, so that the robot is able to learn the communication skill under the learning with human. And also the robot can learn the living environment like a human baby do, right? Human babies are born without knowing anything. But by making an interaction with his or her caregivers, I mean the parents, they get to understand the living environment, world, and also communication skills to handle in the surroundings. So we expect robots to behave like the human, right? To do so, we are trying to install good AIs or machine learning techniques in robots. Okay, yeah, the AIs, artificial intelligence, it is defined like this. It is human-like intelligence realized by computers, and it was first introduced about 80 years ago as a neural model, and then the AI or artificial intelligence was firstly invented or defined by in a Dartmouth workshop in 1956. And then after the introduction of the perceptron, the ability of the machine learning has been greatly the increased. Yes, and then now we have pretty good machine learning techniques these days as a deep learning and something more. Okay, and this shows some brief story of artificial intelligence, and then yes, in Japan we have mainly so far Japanese professors and researchers have been contributed rather theoretically and mathematically for the construction of the mathematical model of the machine learning so far. And Professor Oteru is my supervisor on my college studies, and he already passed away. And I started the research of AIs from the mid 1980s. Yeah. And okay, then why the machine learning techniques works pretty good? Okay, I show you one example. Here, suppose that we have one picture over full HD. The full HD has the pixels 2K multiplied by 1K, right? And each pixel has 8 bits and 3 colors, right? So the total amount of information given by one picture is 8, here, about 50 megabit, right? Then if we consider 1 second moving picture with a frame rate of 30 frames per sec, then the total amount of the information to be transmitted from 1 second full HD movie is 1.5 gigabits. Wow, great amount. Then we can calculate how many possible moving pictures can be made by this amount of information. We can calculate it. 2 to 1.5 giga, right? This is a calculation. Possible pictures, moving pictures of 1 sec video, right? It is this variations, great amount. For example, in the comparison, number of atoms in the universe is approximately 10 to 80, much smaller than this one. So you have a picture, but the possible number of the pictures is this amount, 2 to 1.5 giga, great. So the difficulty of understanding picture is not easy. Before the deep learning, many information scientists has been trying to construct very good algorithms for understanding some object in pictures. But we have recognized that there are pretty big difficulty for flexibly understanding what is described in a picture or moving pictures. But thanks to the machine learning, especially deep learning, and these machine learning techniques, the machine learning works pretty good for understanding, especially pictures and also auditory signals and something more. Okay, then this shows the comparison of the brain and the computer. Here I show some capacities of human brain and computers. And it is said that in human brain, we have about 100 billion neurons and 30 trillion synapses. On the other hand, in the recent PCs, we have about billions of RAMs and also trillion bytes of, terabytes SSDs, right? And somehow, these, from the viewpoint of the calculation capacity, the number of the neurons or bits are almost equal with each other, right? And the element size is mostly the same, and the energy consumption is also not a big difference. But what is interesting is that in the case of a human, as many as we use our brain, the temperature is kept around 36 degrees. It won't go up to 40 degrees or something. On the other hand, in the computers, if you make a very good calculation like deep learning, calculation learning, and the pretty difficult calculation, the temperature goes up for gridding something. It means that the computer CPUs works good, but on the other hand, most of the powers consumed by the calculation is radiated as a heat. This means that the efficiency of the calculation of these computers are not very good, like human or biological systems. And also the other things for communication or data translation or transmission, we have pretty different methods we have. The biological system has a parallel processing. On the other hand, in the computers, the computers these days, we use the serial computation, but by increasing the number of clocks, right, with several gigahertz. So it means that it can make a calculation about tens gigatimes per sec. And by increasing this, the clock speed, we can make the calculation much faster. This is a basic, idea for these calculation. But these are different things. So by, realizing, if we can realize some, new method to work as biological systems, we may be able to realize much better, calculation machines in the future, I expect. Yeah, okay. Yes, the neural network, the structure of the neural network is something like this. And it has multiple layers like this. And in each layer, we set cells for the, transmitting information in each layer. Why? It is because this model refers to human neural model. Human neuron is constructed like this by accepting some, the ionic information from the other cells. Then the potential of the neuron potential in the cell body is working, and then once it exceeds some threshold, then output is gone to the next one. So this the behavior is replicated in the calculation system as a neural network like this. Okay, this is a simple model of a neuron by accepting plural inputs from the other cell. Then when the threshold, the internal potential goes up, exceeds some threshold, then output comes out. Okay, with this structure, this is a pretty simple structure, but what is interesting is that by using this structure, we can construct logics as we use in computers like this. For example, in AND operation, okay, here the weighting function Wi's can be given to this one. In the case of AND, okay, when the input can be 0 and 0, and the 0 multiplied by 1 plus 0 multiplied by 1 equals 0, then it is less than 1.5, then output should be 0, right? And in the case of 1 and 1, then this value can be 2, then the 2 is greater than 1.5, then output should be 1. Then, logic can be defined like this. Okay, here, we can set the two inputs in the x-axis and y-axis. Then AND operation can discriminate these three states and this one state. On the other hand, OR operation is to discriminate this one state from the three states, like this. Just discriminate the status in a linear line, like this. Then, what about exclusive OR operation? Exclusive OR operation outputs 1 when these two inputs are different, right? So it means that the exclusive OR operation to discriminate these two from these two, right? In this case, there is no line that discriminates these two states, right? But, the exclusive OR logic can be realized by using three cells with 2 layers. Okay, this can be one layer, and this can be the second layer. By connecting, multiple cells in, plural layers, the exclusive OR logic can be realized like this. So this means that any logic can be realized by the neural models. And as you know, computers these days can make any calculation by summing up the logics. This means that by accumulating the neuron cells in plural layers, it can execute any calculations as computers are doing, right? Then neural network has been introduced like this. Then in this structure, what is the problem is how we obtain the weighting functions to connect each layer, right? Then about 40 years ago, the back propagation algorithm by Lamelhart was introduced. Then the neural network boom came, right? This is a mathematical calculation. No, maybe this one. This is the mathematical calculation. Okay, this one, yeah. 2 layers like this. It is just a calculation. So you can write a code in a computer. So then the weighting functions can be easily calculated to associate input vectors with the output vectors. Yes, this is what we expect. Yes, right. The neural network can be any nonlinear function, yeah, to associate input vectors with output vectors, right? Then what we have to do is to obtain the weighting functions to connect each layer, right? Then calculation can be made like this. Okay, maybe I skip it, right? And these days, the deep learning works pretty good, but the calculation amount is great amount. Like these days, for example, ChatGPT. Maybe I will present this later. Usually we set several thousand layers, right, for the structure, and in each layer we have multiple cells with the several thousand layers, right? And in each layer, the weighting function among them can be calculated by the deep learning calculations. This is the recent progress of the neural network, and yeah, we have a pretty big boom of deep learning these days, and deep learning was firstly introduced by Geoffrey Hinton in 2006, about 20 years ago. Yeah, 20 years ago. But this network was firstly introduced by Professor Fukushima in 1979 in Japan. Yeah, he's still a researcher. He's 90 some years old. He's still doing research. He introduced in 1979. He introduced neocognitron. Yes, and what he has introduced is that he refers to human vision system. Okay, by introducing two different cells, which is called S cells and C cells. Okay. S cells works for feature extraction in pictures, because he refers to the human vision system, okay, feature. And then C cells works for pulling of the response to sum up, to make some groups arbitrarily, to make some meaning or sense by the combination of the features, right? Okay, maybe this is the example. Okay, these are the pictures introduced in his paper. Maybe I forgot to write. Okay, yeah, yes. In this paper, neocognitron. Okay, here, for example, A, the character A, it has some features. In his network, some feature, the characteristic shape can be automatically obtained by the C cells, like this, right? S cells, right? Then the C cells works to make a good combination to express some, in this case, A character by the combination of the, feature shape of the in the S cells, like this. Then the network outputs that this drawing is read as A. Right? Yes, he proved at that time, 1970s, he introduced this structure of the network mathematically, and he presented the pretty effective performance of the neocognitron at that time. But unluckily, at that time, the computer power is not enough. So he had some limitation of the calculation. So at that time, we didn't have a big boom of the neocognitron. But somehow, in 2006, about 30 years later, the deep learning referred to neocognitron, the structure of the C cells, S cells and C cells. Then, thanks to the computer powers and the big data, found in a network, the network is able to accept uncountable number of data with the quite great number of layers, then the performance of the neocognitron structure works pretty good, they proved. Now we have the big boom of the deep learning. And also, we also have a large language model called LLM. Then large language model is expressed as a series of conditional probabilities. Then this LLM model predicts the next word from a sequence of text. For example, when we have some sequence of the capital of France is, then Y should be the answer. By deferring to the learned data that has been made by having a great number of inputs of texts, then the network answers Paris, right? And yes, the LLM works like that. And it is said that the GPT-4 has been trained with more than 10 trillion words. Yes, word set. It's pretty great, thanks to the computer powers and the network and the structure of the computers and the internet. Yeah, it works. Okay, then okay here, but okay. So what we should be noticed for AIs is that the energy supply is assumed to be infinity. The calculation and the learning and the calculation of the AIs require quite great of electricity. And so far, the energy supply to AI is consumed, is assumed to be infinite. And also, computers cannot be created without computers. We need computers for making computers. And also, even a logic, semiconductors and the logic cannot be created without AIs. So if we want to make a very good AI, the logic computers or semiconductors, we need to use AIs these days, especially these days, right? We have these difficulties. Okay, maybe I don't have so much time, right? Okay, then yes, in the Robotic Research Institute in Waseda University, I'm working there, and yes, and these days, I'm in my laboratory. I'm rather working with not a rigid robot, but a soft robots, using a soft materials and soft actuators and soft sensors, like human or living creatures. Okay, and then maybe let's see. Okay, the one example is the 3D printed biomimetic fingers. Okay, you see, we are printing each parts of human-like fingers by deferring to the 3D model of a real finger that consists of ligaments, bones, tendons, muscles, and so on. And then these days we can print different materials at once. So we print them to make a finger. Then this is articulation with an artificial muscle to move like a human, very flexibly, like this. See, right? What is the difference between the rigid, machines and the soft machines? For when you make once you make rigid machines with the geometry of machine structure, then we have a rigid bar and the motors, rotating motors. Then, for example, the path can be all calculated mathematically, geometrically, right, with a rigid robot. But in the case of the soft robot, for example, our hand, our junction is not rigid. We can move very flexibly with one junction. So this means that when we locate this hand here, the location of the elbow or shoulder can be differently defined or placed like this. In the case of the rigid robot, it won't happen. Every motion or moving path can be geometrically calculated. But in the case of the soft robot, it is not like that. So the idea for controlling soft tissues is to use machine learning, right? Then also the motion of the finger is realized by artificial muscle, but the control is made by a machine learning. Okay. And also we have different topics like tactile display or waterborne actuators to move in water, and or what? Many of them we have in my laboratory. I have different topics like to replicate this one replicates the motion of the insect. Insect, this one. Yes, and also we are developing a fish robot. This is a robot, but it is made of a very soft fin, and it swims like that. And also we are working with inchworm robot to flexibly move to walk like this. And I briefly introduce some of the control of such robot. Okay, the first one is a talking robot. Okay, that speaks like a human. Okay, mostly you can listen to a human-like voice from your mobile phones or TVs or something. But all of such voices are made by software method using computer algorithms. But what we are trying to do is to reproduce all mechanically like a human vocal system. Okay. And also we refer to the physical simulation. And okay, this is a robot. Okay, our robot consists of lung with an air tank and the vocal cords to make a vibratory sound, and resonance tube as a mouth, and the tongue inside, and the nasal cavity, so that the air is led to resonance the mouth tube and the nasal cavity to make a resonance characteristics. And then generated voice is listened by a microphone. This is not for singing, but listening to its voice for the comparison of real human voice. Then what we do is to let the robot listen to its voice and also human real voice for reference, and to make an autonomous control of the motion inside the mouth to make the close sound to a real human voice. It refers to the procedure that the human baby learns its voice. Human babies get to learn the clear vocalization by the training with their caregivers or parents. Firstly, the babies only cries, but gradually the babies learn how to make sounds. But the babies cannot see inside the mouth. But for the articulation, the baby has to move the inner mouth. They are doing not to observe the inner mouth shape, but only listen. Then make a trial to make a close sounds by adaptively moving their mouth, right? This is what this robot is doing. Okay, everything is made by all mechanically. We use a silicone rubber mouth and the tongue, the teeth, and the nasal cavity with a plaster. And then the motors are settled underneath this tube. Okay, the size is the same with the human vocal cords with a length of 18 centimeters, because if you have a different length or diameter of the mouth, the resonance characteristics should be different from the real human. So we all made it in the same or close to a real human with the length of 18 centimeters and the diameter of 35 centimeters or something of the diameter. Okay, then as you see, this robot is able to make a different resonance characteristics by randomly moving the vocal tract, right? And this is the vocal cords to make a vibration with the air. Okay, then then the learning here we use self-organizing neural network, so that the input vector, which is given by the acoustic feature of voice, vocal sound, then output is set as the articulation of the motors. So this network learns how to control the motors to be associated with the input vocal features, vocal sounds. Then the learning has been conducted, yes, for the learning. And then as a result, the robot successfully learns to vocalize. Okay, like this maybe. Okay. Here, firstly, the robot learns the pitch, the different the pitch. Okay. After the learning of the pitch, then it starts. Okay. It sings a Japanese folk song. Maybe you don't know, but all Japanese people know this song and they recognize this singing. Yeah, it looks stupid, but this is the first one who that realized the autonomous learning of human vocal system, all mechanically, and feedback control. This is the first one with all soft tissues. Yeah, no, not hard one. And this robot has been applied for the training system of the deaf people. Deaf people is not able to listen to their voice, so they cannot speak. No one will make a training of the motion of the inner mouth. So deaf people cannot speak. So by referring to the robotic motion, and then she imagined how her inner mouth can be moved by the muscle articulation. Then she makes a training with this robot. And also, vocal features are in real time mapped how close to the target voice is. Okay, each she vocalizes, the vocalized sound is mapped in a self-organizing map. Then he recognizes how the vocalized voice is different from the target one. Then by the training with the motion of the robot and the mapping of the acoustic features, she gets to learn how to make a clear voice with this robotic system. Okay, the next topic is, briefly, the robotic fish. Okay, we have developed a very soft robotic fish with a soft fin like this. But what was the problem is that the soft fin is not controllable, especially in water. Yeah, and it swings with different frequencies of the soft actuators, and the relation between the control command and the swimming performance is pretty uncertain. So what we try to do is to associate the control parameters with the generated swimming behavior with a neural network by using a neural network. Then it was successful. Then, yes, the fish robot, yes. It is untethered one. Yes, everything is packed into this robot and it moves. It swings like this with a 2 Hertz flipping motion, And also maybe, yes, we have, yes, this is a slow, maybe, okay, let's see, another one. Okay, okay, maybe this one, okay, the slow flipping motion, like this, very slow one, the 1 Hertz flipping motion, and faster. Yes, 2 Hertz flipping motion. This fish robot is able to swing with different flipping motion, and it can turn right and it can turn left at any by using the learned control parameters with the flipping motion. Okay, like this. The robot is pretty real, right? Okay, and maybe we okay, and also this is okay, maybe this is the first one. Continuum robot for flexible object grasping. Okay, we are developing also a long, tail-like robot for grasping objects. Okay, like this. We construct this with flexible robot with a ball joint and the spring and pulling actuators. Okay, like this. Okay, maybe yes, like this. Yes, it can move like this. Okay, like this. It moves by pulling the tendons. But what is the problem is that when we like to put the tip of the robot in some location, there are different possible the shape of the robot. Right. Yes. So we also apply a neural network for the learning of this flexible motion. Then yes, and then it able to grasp like this. Okay. Yes, with a different style of the grasping, like this, all learned by the machine learning. Yes. Okay. Maybe it's time to I have some other examples, but it's time to. So maybe okay. Yes. Yes. Okay. The conclusion is that I have introduced some mechanical or soft system to grow up or to learn like human behavior. Okay. Yes. Maybe that's all. Thank you very much. These are my research group with my students. Thank you very much.
So we have time for some question.
Yes.
Thank you for very nice presentation. I'm wondering, how do you explain? You said that this is explainable AI for your fish and human robot. How your explain tools used in this control? Thanks.
Explain is okay. I'm in my laboratory. We are also working to explain how it learns. Okay. For the one of the explaining method is to use a feature map, self-organizing feature map. We set the self-organizing feature map in between the some layers. Then in the feature map, some relation of the patterns are mapped in the feature map, so that the cross patterns are mapped close with each other, and the different patterns are located far with each other. By referring to the topological relation that has been automatically constructed in the map, we can see what relation the learning result is obtained.
Okay, makes sense. So you mean you can identify what the features find by the machine learning?
Yes.
Yes. And
yes.
Do you use this information to optimize the control or optimize the learning?
Okay,
learning process.
I see. Okay, from the viewpoint of the optimization, so far in the application of the control of soft robots, we do not think of that. We do not consider the optimization because in the human behavior, I don't think we have optimized motion or behavior. Humans are doing some behavior without explanation, right?
Yes.
So what is good for the soft robot like fish or a rolling ball or a speaking robot? What is the result is how human understand it, how human considers satisfied or something. So satisfactory or the satisfactory by human can be one measure for the evaluation of the results. We think.
Yeah, agree, yeah. But I think maybe if we can get the explainable information, maybe we can help accelerate the learning. It is possible?
Yes,
For
it can be
example, for the
possible.
human, for the baby, if we know how the baby learn it, maybe
Yes.
we can give more, do some optimization, make the baby learn it fast.
Yes. As I just mentioned, okay, here, let's see. Okay, the speaking results. Okay, yes, maybe. Okay, this one. Okay, the robot learned the transition from R voice to E voice. Okay, the motion of the articulatory motion smoothly moved to R to E. So we can recognize that this learning was successfully made. For example, this is a performance from R sound to E, R, E, E. Okay. In the case of human R to E voice, from R voice we open the lips and the deep location is narrowed. But on the other hand, E sound, E is pull your lip, and the deep side opens. So this motion has been automatically obtained by the robot. So this kind of the motion is understood by the satisfactorily obtained. Yes. So this is one of the evaluations that we have for the after the performance of the learning. Is it okay?
Yeah, okay, thank you.
Thanks for the nice talk. I was wondering about the dynamics. When we have neural networks, that is a mapping of the inputs and the outputs.
Yes.
So how are you characterizing the dynamics with the neural network? So let's say the sampling time of the system, or how are you considering the sampling time of the system or the time constants of the system within the neural network?
I see. In fact, it depends. For example, this speaking robot, sampling frequency is set as the voice sampling ratio. Like in this case, I see 10 kilohertz for the vocal sounds, and each sound is mapped into the motion of the motion of the robot. And on the other hand, in the case of the fish robot, the sampling frequency is not very fast, like video sampling rate, 30 hertz. So it depends on what kind of information to be given to the robot. It depends for the control of the robots. Yes.
Thank you so much for the presentation. Thought it was very interesting. One of the things that is interesting, as you mentioned, of using machine learning and other adaptive mechanisms to learn the model web instead of having to define the functions that you can apply to this complex problems.
Yeah.
But do you try to afterwards extract a physical function, for example, a differential equation would represent this dynamics?
Maybe we will do it. Okay. What we are doing is to apply reservoir computing method. I'm also working with a scientist of the reservoir computation, and I belong to the Department of Physics. So this kind of nonlinear function obtained by the neural network can be associated with a reservoir computation. It is all physically constructed in a reservoir. So yes, we will now working for the reservoir computation. Yes.
Okay, because I was thinking in terms of security. For example, you're moving a hand.
Yes.
And if you learn a model that has a lot of parameters,
Yes.
you might not know what are all the possible outputs, and
Yeah.
you might react in a very strange way in a certain moment.
Yeah, that's
For
right.
example,
Yeah.
You have a human, and suddenly, now I was seeing all these videos in China of suddenly the robots
Yes.
following people or
Yeah.
attacking people.
Oh.
When this can happen, and given input parameters that are not known.
I see. Yeah. In fact, it depends on how much complexity the robot will do for dealing some objects. Just to make some gestures, it's okay. But if you like to, manipulate some, for example, mobile phone or some chopsticks or something, you need much more, much complex, articulations of the finger, right? So this is what we are trying to do, not just simply, motion, but also to manipulate something for supporting human.
Okay, thank you.
Thank you very much.
I think that then we can thank again the speaker.